Um, so just a quick reminder that on Wednesday I'll have like extra office hours. So just feel free to stop by if you want to ask me something before the exam, which is on Thursday. I'll still be checking the email if something, if you have any questions before or after Wednesday or before the exam. But I mean, it's always like just easier to ask them in person. Like, so officially they're like from 2 to 5, but if there are a few people around, I could just stay longer. Like, so, and you can check the location on the announcement, but I think I sent it today again, like it's somewhere on Bush, like if I'm not mistaken, for the office hours. The final exam, I think, is the auditorium on Beck Hall here in Livingston. So just be sure to be there, like from 4 to 7. In terms of topics, like the only thing that I said is that's left to discuss is like the divergence theorem. I'll tell you what the Stokes theorem is, but I won't ask that one on the exam just because it is a bit trickier to kind of like wrap your head around. So it's a bit too much, I feel like, to do both on the same day. But I'll still kind of like give you the formula, tell you what it's good for and that stuff. You can check like previous recorded videos if you want to see some more examples of Stokes and things like that. But divergence is kind of good enough. So that divergence theorem is related to flux, which is the last topic we were discussing last time. So the idea about flux, just to remind you what it is. So what you have to think is that you have a surface in space. Okay, so here you have a surface S. And there's like, you can think about it as some sort of like fluid passing through the surface. So you can draw some curves, which kind of represents how the fluid is moving. So that could be air, water. It could also be like a swarm of bees. Like it could be like any sort of like substance that can move in a sense. So and so there's like kind of a vector that directs the substance. So that vector I'm calling F. So you would think about it typically as like the, as the velocity of the fluid in a sense. But like in other cases, like these could be, for example, like a magnetic field, and these are called the field lines. Like the curves themselves are called like the field lines to the magnetic field. So there are like many different interpretations for what this can be. But so I'm just thinking of F as kind of like a vector that directs how these curves look like. And so there's some stuff of this material that will pass through the surface, and that's related to the flux. And the way I told you we could find the flux last time is that you take the dot product between this vector and a vector perpendicular to the surface. And integrate that. So the vector that ends up being perpendicular to the surface, if you parameterize it, is something like this. I'll do some more examples today about like flux. So I'll remind you then how to do this concretely. But in practice, like the way that like how the integral looks like is like you take the dot product between this vector that directs the flow of the substance with the normal vector to the surface and integrate that out over the surface. So this is normal vector to the surface. Okay. So any flux in this case, it's like I should call this flux of F. So the flux happens to be like it is a double integral of sorts. What the divergence theorem says is that in certain circumstances, you can compute the double integral in terms of a triple integral when the surface happens to be closed. So we do have to kind of like make a small detour of surfaces, just the difference between being a closed surface versus not being closed. So like the opposite for us of being a closed surface is kind of like a surface with boundary. So let me just draw some pictures first. So this is, I should say that there are two types. So okay, so the easiest ones to describe maybe are like the ones with boundary. So a surface with boundary is literally what it sounds like. It is a surface that has a sort of edge. So for example, here is a surface with an edge. Like, so if you take a cylinder, right, like this bottle of water, like you see like the edge right here, right? So if you're walking on the cylinder, right, like if you're like an ant walking on the cylinder, you can reach the end of the surface. So it's kind of, let's do some pictures of surfaces with edges. So, or with boundaries, sorry. Like, let's call this boundary slash edge. So these are easier to discuss, and then the others are like the ones that don't have that property. So here's like some examples of surfaces with boundary. One is so one is like kind of a cylinder where you can think of it as some sort of bottle, but then I'm just including the bottom of the cylinder maybe to, yeah, like, you know, so like let's just think about this as a part of a cylinder together with the bottom disc, but no top, right? So if there's no top, that means if you're walking along the surface, along this bottle, you can reach the edge, which is like this like circle that you see here on the top. So here is one example is the cylinder, like a finite cylinder with the bottom disk included. I'll put the edge on with a different color to kind of emphasize that. So what I'm saying here is that the edge of the cylinder um, would be this top circle. Why is the bottom circle not part of the edge? Because I'm kind of closing it with a disc, right? So once you get here, reach here, like you can kind of keep walking along, you know, through the disc. So like if you thought about it as like, you know, you're driving, like again, like an ant, the ant can move, you know, downstairs through the disc. So that's why you wouldn't, like, you know, if you drill a hole and remove the disc, the bottom disc, then now like the edges are like the top circle on the bottom circle, right? So like that, then it would have two edges. Another surface with edges or boundary is just like a piece of paper, like literally. So like you can have a finite plane. So another one is a finite plane, right? Because if you have a finite plane, then what are the edges? Like these three, like, sorry, four line segments, right? Which is like the flat earth model, right? So if you're a flat earther, like the point is that it was an end of the world, right? Like you were afraid to reach this point because like then you don't know what happens. So in fact, like the exact opposite, like in that sense from a surface with boundary is something without boundary, like the opposite of this would be something like the sphere. So actually, if you look at a sphere, let's put something without boundary because that's a nice comparison to have. Surfaces without a sphere the entire sphere, right, like has no boundary. Okay, because if you walk on the surface of the sphere, there's really no place where you kind of reach the end. That's the idea of like that's the idea of having no boundary, that there's no place where you say, oh, if I keep walking, I kind of like reach into the void. So with a sphere, like you don't have that problem. Then there are things that you can kind of fix to make them without boundary. So for example, you could take like an ice cream cone, right? So you could draw a cone. So if you have a cone like this, it does have a boundary, which is this top circle, but there are ways to fix it. Like one way to fix it is just to kind of like add like a disc on the top, right? So like a cone with disc that has no edge anymore. Like you kind of like once you reach the original edge, which was the circle, you can just now keep walking on the disc. So cone with disc. You can do something more like closer to like an actual ice cream cone, which is like to put like a cone together with like an ice cream ball. So like kind of like have a sphere, like or like so you can have something like this. So now, once you were supposed to reach the original edge, which was a circle, now you just walk through this, like keep walking through half the sphere, and that also like removes the edge. So come with half a sphere. So does that make sense? So like many examples that you could think have like edges. There is kind of like a way to add things to them, so the edges get removed, and that's one way to make a surface without a boundary, just like adding things onto it. But the point is that we kind of, for what I'm going to say in a moment, we are interested in surfaces without boundary because once you have a surface without boundary, then there is like a region that gets enclosed by it, right? So once something has like no boundaries, then there's like a 3D region that has that surface as kind of like its exterior wall, which does not happen, which doesn't really happen like in one of the previous cases. Like if you look at the bottle, if you look at the bottle and you ask, oh, what's the region enclosed by the bottle? Okay, you probably want to say like kind of the inside of the bottle, but there's really no inside until you put like the top lid. Because you can just keep putting like your fingers inside and outside the bottle, like whatever. So like it's not closed. I mean, until it's closed up, there's really no way to properly say that there's like a region enclosed by it. It kind of doesn't make sense. So in the divergence theorem, what we want to say is that the flux through a closed surface equals a triple integral of something called the divergence and that takes place over the region enclosed by it. So that's why we need to work with closed surfaces first to begin with. Because otherwise, like it's like the plane is kind of like an extreme example. Like if you ask what's the region enclosed by a plane, there's not like a obvious answer in any way, right? So this one is a bit like extreme, but the cylinder without like one of the like at the top part, it kind of makes more sense. And many times you secretly are thinking about closing them off when you would do like the integral, but really here you'll see it's important to kind of work with something closed off so that we can do like a triple integral properly. Is that making sense? Okay, so maybe before doing the example, let me just tell you what the divergence of a vector is, because that will appear in the divergence theorem. It's actually very easy to find. So And I'll show you some animations and I'll tell you what the divergence theorem says. So what is the divergence of a vector? So if you think of the vector, so the divergence will be a scalar. So this is going to be a scalar. Meaning that it's a number. So you're not, you will get a number or like a function as the answer. So number function. It will not have entries. That's what I'm trying to say. So if you have a vector f, well, being a vector, it has entries. So I'm calling the entries f1, f2, f3. So this like the first entry, the second entry, the third entry. And the divergence of f. So this is what this what we'll write as a divergence. So this. Okay, so the way you to remember how to find it, the way you think about it is essentially in the way the notation is suggesting as some sort of dot product. Okay, so this triangle thing is stuff that has been appearing with gradient and with curl. So it is a representative of like the partial derivatives. So think about this as like the partial derivatives. And f is just in terms of its entries, f1, f2, f3. Okay. But then you want to do the dot product between these two things. So you have to ask, well, what does it mean to take a dot product? So naively, if you just like kind of multiply them, then you have to think, what does it mean to multiply them? And the interpretation here for multiplication is just to take the partial derivative of f1 with respect to x, for example. So you do the partial derivative with respect to x of f1, and you add the partial derivative with respect to y of f2, and you add the partial derivative with respect to z of f3. So the divergence is the way that the formula works. It is as a sort of like sum of partial derivatives, but the partial derivatives like that you add are pretty simple. It's like the first entry with respect to x, the second entry with respect to y, the third entry with respect to z. So and then you just add out all of them together. Okay, so let me do some examples first to show you how it looks like. But it is significantly easier to find the divergence of a vector than the curl because the curl involves this product thing. Yeah.
What is the exclusion behind why the dot product gives that the divergence and the cross product gives the curl?
Okay, so it's not it's kind of like the first thing is that like the better way to think about this is like that like how do you end up defining something like this, right? It's not obvious. So really like the way you kind of like think about these like problems, like if we had more time, we would kind of do like a more hands-on approach. We actually end up finding the divergence, which is like the cool thing to do. But the idea is like what you end up doing is like if you had a cube, right? Like if you have like a box with the six sides, that is like a closed surface, right? And then you would find like you would take like a kind of like you would try to compute directly by brute force the flux of like a vector through this cube. And for the case of a cube, if the cube is small enough and you do like some sort of Taylor approximation, what you find is like, oh, that actually happens to be, which is what I'll write in a second, the triple integral of something, and that something happens to be the sum of partial derivatives, right? So like the reason why this comes, like the way this appears is just because it appears when you kind of like check it out on a specific case, and you just realize, oh, the flux ends up like agreeing with integrating this thing on like on inside the cube, for example. Okay, so like you kind of like you kind of find out this quantity first, right? Like, and in fact, that is kind of, you could just write it like that. Like, so for example, that is like the way Maxwell would write it. Like, he didn't like use this notation. This is kind of like a later invention, like Heaviside and like other people. So like you could just have written this, like, um, like that. But what you realize, yeah, is that it does happen to coincide with formally like a dot product between this operator and the vector. But that, like, there is not so like such an obvious way to anticipate that, like, why the divergence had to do with the dot product and the other one had to do like with a cross product, right? Like you kind of like you could just have tried to write it out, like you kind of write it out explicitly first, and then like as a memorization skill, like you can realize, oh, it actually can be rewritten as a dot product of sorts, if you know what I mean. But yeah, it's not, of course, like you do like, it has to be like a triple integral of a function. Like, so a dot product does produce like a function, like, or a scalar. So that is why it's more related to a dot product than like a cross product. But besides that, yeah, it was not obvious, like, like it could have been like a length, for example, to give you like a stupid example, like, you could have been like, okay, what's another thing that's like a scalar, the length of a vector, right? So it could have been, oh, maybe you have to take the length of these partial derivatives or whatever. Like, there was no way to know until you kind of like check it first for like a cube, or which is how you kind of like really find these things first. So there's actually like a very cute book, if someone really wants to learn all this stuff properly, not like 2 weeks of classes, like, which is called Deep Curl and all that. Um, it's like a very small book, like maybe 100 pages, like a short book. But it kind of goes through all these, like being derived, like from a physical perspective, like fluid dynamics interpretation, and then you do get like a lot of insight on where these formulas come from, because they kind of like start more like, okay, let's try to find out the formula, instead of like just like handing it out like from the sky, which is what we're kind of doing now. But yeah, like there's like the only thing for sure is like it had to be like a scalar, and the easiest way to produce a scalar is kind of like with a dot product for us. But right, besides that, it's not obvious why it had to work that way until you kind of do the calculations. Um, but yeah, like that is actually like a pretty good book that does go more into those like explanations of why this and not this other thing. Um, so okay, let me do some examples of divergence, like, and then I'll show you how it looks like on the animations, and then I'll tell you what the divergence theorem says. Okay, so here's some examples. They're really easy to find. So let's say that your vector is that. What is the divergence? The divergence is just take the partial derivative of the first entry with respect to x, take the partial derivative of the second entry with respect to y, so it's more or less alphabetical. And then take the partial derivative of the third entry with respect to z, and add all of those things together. So it's like so it is again like a dot product of sorts, but this gives you 2x, this gives you x actually, and that gives you 3z squared, and so you get 3x plus 3z squared. So that is an example, like here's another one, it can also come out just to be like an actual like single number, so like you could have something like z, which I'll do in a bit, I think. Like negative y x z. So if you take something like that, what is the divergence of this vector? You take the derivative with respect to x of the first entry, the derivative with respect to y of the second entry, and then the derivative with respect to z of the third entry. And then you add up all of those together. So again, it's always like alphabetical in terms of like the derivatives. First entry with x, second entry with y, third entry with z. And so here you get 0 plus 0 plus 1, and then you get 1. Okay. And then just to do one more. Like there's really, it's just like adding a bunch of partial derivatives, but there's not much to say in terms of how to do it, but at least I should put another one. So you get yz plus 0 plus 3x. If you prefer to write it. Okay, so again, like you take the corresponding partial derivative of each entry and then you add them up. Yeah. So notice like E is like a scalar or a function, like really it has no entry. So it's just like a single expression. It does depend on x, y, and z, but like itself, it doesn't like it's not like a curl. The curl had like first component, second component, third component. The divergence is just like um, a scalar. Okay. So let me show you a little bit of how it looks like. Yeah, it's just kind of useful before telling you what the divergence term says. Oh, this one is cute. It's a nice animation. Is that okay? Are there any questions about how I found them? So this one compares I love this. I think this is the one that I love. There's a bunch of stuff being shown here. Let's see. Okay, let's see. Let me see like the other ones. Okay, this one is less confusing. Yeah. Okay, so for example, you have a vector, but you think about it as a fluid, so you kind of think about these arrows as telling you how the fluid moves. And the idea with the divergence, so here like it's easy to compute, for example, that the divergence is always 2. Maybe I should find something like an example of a field where the divergence is not constant. Okay, this is look at it. Okay, so I like this one more because it kind of changes from point to point. So the divergence, if you find like, the vector is x comma y squared, so if you find the divergence, the derivative with respect to x is 1 and the derivative with respect to y is 2y, right? So like the divergence for this one is just 1 plus 2y. That's kind of what you get. So that means that at the point x comma y, the value is 1 plus 2y. So the value for the divergence does depend on the height, but at constant height, like the divergence should be the same. So if I kind of try to move this at a constant height, you see like the divergence almost remains like around 3 for this line, for example. Okay. And then what is the idea of the divergence? Like, and then you see like it's increasing with the height, right? So like it becomes higher with the height. So if you think about it as a fluid, it's kind of telling you that, you know, if you had if you had kind of like a disk around it, there's kind of more, you know, there's kind of like near this disk, there's kind of like a net production of particles happening in the sense that, you know, there's kind of more stuff. It's kind of like if you think about it as a bathtub, that there is you know, you are kind of adding like water into the bathtub at this point. So there's like that would push the particles out, and then there's like a net outward flux of like stuff through this circle. So if the divergence is positive, that's what's called like a source, in the sense that you're kind of like adding stuff into the fluid. Whereas if the divergence is negative, it's there, oh, like this should be so that the y square is always like negative. Whereas when the divergence is negative, then there is like what you would call like a sink, meaning that there is like kind of like you're draining water from the fluid. So let's see if there's one that's a little bit better for that. Well, I mean, you kind of have to move it around, but the like positive divergence just means that near that point, somehow like stuff is being added to the fluid, and negative divergence means that near that point, stuff is kind of being removed from the fluid. So in the, you know, there is like, for example, these. Oh, like this is a good segue for like the Maxwell equations. Like one of the Maxwell equations is essentially that. I think we can go there to open them. So like, well, there are four equations. Two are for the divergence, two are for the curl. Like, but so for example, you see this, it says like the divergence of the electric field is like basically the charge density divided by a universal constant. So what you interpret that to mean is like kind of like the electric field is like a field, which you can think about it like analogous to a fluid. And then like the electric charge kind of produces or destroys like the fluid, which is the electric field. So like if it's like a positive charge, that's positive divergence. So that's why when you draw these electric fields for like a positive charge, like the electric field is pointing away from the charge, because it's kind of like a charge there is kind of like creating electric field in some way. Whereas if the charge is negative, then it is a sink. So it's kind of like the field lines kind of want to go towards the electric charge, the negative electric charge. So it acts like a sink. If you want to do like a fluid dynamics analogy, or like in terms of a bathtub. Whereas for something like magnetic field, the divergence is always zero. I don't know if you remember that when I brought the magnets, like if you played around with it, you would see that the field lines close out. And so the interpretation of that is that there's no like analog of a magnetic charge for magnetism. So then like if you saw like the videos that I posted on Canvas, that means that there are no magnetic monopoles. And if you find one, you get like a Nobel Prize for physics and many other things. Because like but like it's kind of saying there's no analog of like an electron or or a proton for like a magnetic field, like something like a single charge that would produce magnetic field, like. So that's why it's always divergence free. And the other name for like a divergence free vector is solenoidal or incompressible. So it just means like fluid is incompressible, for example, if the divergence is zero, which means that kind of like the mass is conserved of the fluid. So again, like there are many like cute analogies here with fluid dynamics and all that stuff. But the point is like the way to think about what this divergence thing is that if the divergence is positive at a point, it's kind of like stuff is being generated at that point. And if the divergence is negative at a point, it's kind of stuff is being removed from that area, from that region of space, in some sense of the word, okay? So in terms of a bathtub, it's literally that you would open like the water, like you would pour in water at a point where the divergence is positive, and you would remove water at a point where the divergence is negative. So you create like a sink, essentially. Okay. Okay, so let me tell you what the divergence theorem says, and then we can do like an example to show how it works in practice. It is very simple here. Let's see where I can. Let's not erase the formula because it's kind of useful to have it in around. This is also called Gauss's theorem, but I'll refer to it more just like as the divergence theorem. So what it says is that if you have a closed surface, right? There's a Gauss law in electricity and magnetism, which uses the divergence theorem. So like so very confusing. So that's why I just better to call it the divergence theorem. So if you have a closed surface, so here this is a closed surface. And you have a vector f, right? Which again, like can represent like the it's representing maybe how like a fluid that's moving through the surface moves. Like so maybe the fluid goes like this, like that. Okay. What the divergence theorem says is that the flux of F through the surface, the flux of F through the surface through the surface equals if instead of doing the flux directly, which again we can compute directly, and I'll show you how to do it in a second. But what the divergence theorem says is that that flux has to equal the integral of the divergence of F through on the region enclosed by the surface. So here, this is going to be equal to a triple integral of what? Of the divergence of F. And here R is the region enclosed by the surface. And maybe I have to put this somewhere. When we find the flux here, we put we use a normal vector that points away from the from R. So R here, and for the flux, and we put it as a remark. It's kind of important. For the flux, we choose a vector. And we choose a vector which points away from R.
So I saw something where it was with like that equation,
Mhm.
treat the divergence of that. Kind of think of it as like a divergent density thing.
Right, right.
Like,
Yes, it's like a flux density.
Yeah.
Yeah.
so is that, that would be like the flux at each individual point, and then we're doing it for like the whole
Right.
bounded area.
Correct, because I think it's like, you know, it is it's like, it's similar with mass, like if you. Where mass is like the integral of the mass density times the volume. So by analogy, whenever you integrate something over a volume, it is a density of sorts. But here, because instead of like mass, you're putting flux, you're saying that flux is kind of like an triple integral of the divergence. So the divergence has to be like some sort of like flux per unit volume, if that makes sense. So it's yeah, so like the divergence, like because of this theorem, like the divergence, you can think about it somehow like as flux per unit volume, if you like. Um, Which is sort of how you, like, again, if you did this like the right way, you would kind of find it out because you check this on a cube. And on a cube, like if you do some Taylor expansion, blah, 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 like you kind of like see it explicitly appear. So in this book, diff curl and that, yeah, that's kind of like the definition of divergence that they give. Like it's kind of like by definition flux per unit volume, and then you just find the formula that the formula has to be this. So but yeah, like it is like some sort of density if you want to think about it, I would think. Uh, Is that okay? So let me do an example to show you how to find the flux without knowing the divergence theorem and how to find the flux after you know the divergence theorem, so that you can see how much of your life is in terms of time is saved with the knowledge of the divergence theorem. So so okay, let's say our vector is this one. Not too complicated, and the surface is going to be so it's going to be the paraboloid. Uh, Between together with the together with the unit disk at height 1. So give you a second to write that down and then I'll do a picture. Okay, so what is a paraboloid? The paraboloid looks like some sort of like salad bowl, right? We have talked about it before. So it looks like this. The thing is like the paraboloid on its own, it grows indefinitely, right? If you don't put any restrictions to it. So that's why I'm saying here, oh, we're just looking at the paraboloid between z equals 0 and z equals 1. So that means that we are ignoring everything after height 1 so that the paraboloid is finite in size, if that makes sense. Now, if you look at the paraboloid, at that finite paraboloid, it does have an edge, right? Because it's the circle at height 1. So to close it off, which is what we started talking about today earlier, I'm going to close it off by kind of like putting like a disk at the top of it, of height 1. So like here I have the disk at height 1. It's the disk. Okay, and this finite parabola together with the lid, this um, is a closed surface, if that makes sense. Um, now there is a region enclosed by it. Before, if you don't add the disk, then there's no region enclosed by it. Yeah. So because it is a closed surface, just to make the pictures here, when we find, I'm going to find the flux for F. So fine, like I should have said here, I want to find the flux of F through this surface. Okay, so when it's a closed surface, the convention will be to choose a normal vector that points away from the surface, or away from the region enclosed by the surface, I should say. So that's why sometimes it is called outwards flux, because you're using the vector that points away of the surface. Otherwise, it would be called like inwards flux if you were using the vector, the normal vector that points towards the surface or towards the inside of the surface. So that's how the normal vectors have to look like in this case, and you'll see from like where that plays a difference in the parameterization when we try to compute the flux. Okay. So I'm going to find, again, just to kind of show you the advantages of having the divergence theorem and to practice some more flux calculations, I'm going to do the flux first without using the divergence theorem at all. So I'll find the flux without the help of the divergence theorem, and then I'll do it with the help of the divergence theorem so that you can see how they differ. So I'm going to find the flux without the help of the divergence theorem. So if you don't have the help of the divergence theorem, how do you find the flux? You would say that the flux, can you find the flux? This surface really has two pieces, like the top disk and the parabolic part. So you would say that the flux is the flux through the disk plus the flux through the paraboloid. And then you have to find each of those individually. Okay, so what I want to say that the flux is the flux through disk plus the flux through the paraboloid. Okay, so let's find first the flux through the disk. Okay, so here's a reminder of how do you do that from last week. To find the flux directly, you need a parameterization of the surface first. So let's parameterize the disk. So let's parameterize the disk. What does it mean to parameterize the disk? That if you take a point on the disk, okay, if I take a point on the disk, I have to write it in terms of two parameters, right? Like that's how you parameterize a surface. So a disk, it is naturally, it goes well with polar coordinates. So like an easy parameterization for a disk is in polar. So you can put like that's r cosine, like x is r cosine of theta, y is r sine of theta. And what is z in this case? Like the disk is at height 1, so you can replace z with 1 because it's a constant height. That's kind of like the most important part here, like to note, like notice, because it's height 1. So that, if you notice, like that depends only on two variables, r and theta, and that's why this is like a parameterization in terms of r and theta. So in the notation of last time, what I was writing this as is the position vector as a function of r and theta. Um, is that making sense? By the way, so I posted like the solutions to the workshops on Canvas and the quizzes. I also added like an extra workshop just in case you want to check it out because it had like more extra parameterizations if you want to go through them, which is kind of useful. So like, because all this stuff, surface stuff, if you have the parameterization, really everything is somewhat easy, but without it, like it's a bit problematic. So once you have the parameterization, you can rewrite f in terms of the parameters. So f was negative y x z, but what is y? Y is r sine of theta. So I will put it as negative r sine of theta. What is x? X is r cosine of theta. And what is z? Z is 1. So that's how the vector f looks in terms of the parameterization. And then the last thing that we need is a normal vector to the surface. So we need a normal vector to the surface before finding the flux. So how do you do that? You had to find the partial derivatives of the parameterization with respect to the parameters. So what's the derivative of r with respect to of the position vector with respect to r? You get cosine of theta, sine of theta, comma 0. And what's the derivative of r with respect to theta? It's minus r sine of theta, r cosine of theta, comma 0. So the normal vector was the cross product between these two. So the normal vector is okay. Uh, this one is kind of easy to do. Is 0, 0. And the other one gives you r cosine square of theta plus r sine square of theta. And that's 0, 0. Oh. Let me put in color what the products that we're going to do. Okay, so we're going to do the dot product between those two vectors, and the integral of that will be the plot. Is that okay? Making sense at this point? So two things to notice here is that this, if you see like the third entry is like an R, in polar coordinates, we would always write R d theta. As I mentioned last time, that's where that R comes from. So really, this already incorporates the Jacobian. So there's no, when we do the integral in polar, there's no need to multiply by an extra factor of R because it's already here secretly. Like the cross product comes with the Jacobian in kind of inserted in the entries. So that is kind of like good to go. And the other thing to notice here is that this vector points, R is always non-negative, right? So this vector has a positive third component. So it does match like this picture because we want to choose a vector pointing away from the surface or the region enclosed by the surface. And so we at the level of the disk, we do need something with a positive third entry, right? Has to be pointing at the positive z-axis. So this one does point away from the region enclosed by the surface. Points away from R since the third entry is positive. Because, I'm sorry.
If it didn't point away, would you flip the sign?
Right, the thing is like you could have done the cross product in the opposite order.
Yeah.
If you have done it in the opposite order, you get 0, 0, negative R. So it's flipping the signs, yeah, it's the same as just having done it in the opposite, flipping the order of the cross product. So, for these problems with flux, you do have to check that the cross product was taken in the correct order, just like, by verifying something of that sort. Otherwise, like you would get it out by an overall sign because, but yeah, like you don't have to redo the calculation. You just multiply every entry by -1 if it has come out the wrong way. Actually, it will happen in the next, once we do it in the parabola, you'll see that in that natural, the order I have been doing it, it will come wrong. So we'll fix it. But this one is fine. And so the flux. Okay, so the flux is the integral between these two vectors. So it's the integral between negative R sine of theta, R cosine of theta 1. Because this is F, right? With 0, 0 R, because that's like the normal vector. So flux is always with the normal vector, just as a reminder. So the integral is with respect to the parameters, which are the R and the theta. So, setting the bounds here is not that different from like a typical polar problem. Theta goes from 0 to 2 pi, and it's a disk of radius 1, so it's 0 to 1 for R. And this is like the integral from 0 to 2 pi, 0 to 1 of R, the R, the theta. Okay, and so that just gives you pi. Is that making sense? So that is the flux through the disk. Again, like the total flux is the flux through the disk plus the flux through the paraboloid. So I still have to do the same exact thing for the paraboloid. Okay. But I have to raise here some questions about this before I move on. It's essentially the same sense, but with a different parameterization because now we have to parameterize the paraboloid. Well, let me do it here, show you how it looks like. And then then we'll do it with the help of the divergence theorem and you see how much faster it all becomes. So that's why the divergence theorem is so nice. So if you want the flux through the paraboloid, so again, parameterize it. So step 1 is to parameterize the paraboloid. If you choose a point on the paraboloid, well, it's again like for something like a paraboloid, usually if something has like x squared plus y squared, it's a good idea to just switch to kind of like polar in a sense. So you can like just say that x is r cosine of theta, y is r sine of theta, and what happens with z is x squared plus y squared, so it becomes r squared, right? So that would be the parameterization of the paraboloid in terms of r and theta. Is that okay? So you see, like in this case, compared to the disk, like the only difference is like in the third component. Once you have the parameterization, you can write f in terms of the parameters. So what is f in terms of the parameters? F was like negative y x z. Negative y becomes minus r sine of theta. X is r cosine of theta, and z is r squared. Okay, so that is what that gives you. And the other thing is we need the normal vector. So just as before, we take first the partial derivatives with respect to the parameters. So the derivative with respect to r is cosine of theta, sine of theta, and now it's 2r, right? So before we had a 0 actually here. I'll kind of use the same layout because it's almost exactly the same, but a bit more tricky. So and then you have to do this with respect to theta as well. That's minus r sine of theta, r cosine of theta, comma 0. Okay, so those are the new vectors that you have to use into the cross product. So the normal vector, again, like my first guess is to just use this cross product and you'll see what happens in this case. So it's now cosine sine 2r, and then a negative r cosine, sorry, negative r sine, r cosine, and 0. So the only thing that I changed was this one, but it does have like important effect on what happens next. So this gives you what? It gives you when you do the cross product now, you'll get minus 2r squared cosine of theta, and then you'll get negative 2r squared sine of theta. And the other one is still is like r cosine squared plus r sine squared. So it does continue. The third entry continues to give you r. Okay. But the idea is that this vector has to be pointing away from the region enclosed by the paraboloid, right? Or by the surface, sorry. And if you look at it, like all in this picture, all the normal vectors have like a negative third component. Usually that's the easiest way to check whether the normal vector is correct or not. You just think, oh, is the third component kind of like reasonable in terms of the picture? So all of them, like, if you have the salad bowl here, like all the normal vectors would be kind of pointing towards the floor. So they have to be pointing with negative CX and C entry. But again, this is always positive, so this cannot be the correct one. So you have to flip every single entry to get the correct normal vector, because that means that you have to take it in the opposite order. So this has like, doesn't point the right way, so it should be negative. So we work instead. Like essentially what you're doing is like having taken the cross product in the opposite order. But obviously you don't have to kind of do that calculation again, because if you remember, A cross B is minus B cross A. So it's just like an overall sign. So you do have to flip every single entry, not just the last one. Like that is something like important, because again, like they differ by an overall sign. Okay, and this is the vector that, again, like everyone has like a factor of r, and that's kind of related to the Jacobian thing, so like they all come with the Jacobian incorporated. And now we do the dot product between these two vectors for the flux. So the flux is going to be the bounds are actually the same, like the theta will go from 0 to 2 pi. And the paraboloid, since like it stops at the plane v equals 1, will go from 0 to 1. You are doing minus r sine of theta, or cosine of theta, r squared, dot, let's put this one in yellow. Okay, so if you check the dot product, I kind of chose it so that these two factors would cancel out. So you end up just like integrating, like it will be the integral of negative r squared. Like just checked out that gives you. Because this one will have minus sine cosine and this one will have cosine plus sine cosine. So that the first two factors from the dot product cancel out. So you get minus r cubed, r d theta. Oops. It's over. Let's see the words. So you get minus r cubed d r d theta, and that is minus pi over 2. So what is the total flux? It's the flux through the disk, which is pi, plus the flux through the paraboloid, which is negative pi over 2. So the total net flux is pi over 2. Okay. So it's like it is a long computation. You have to do the parameterizations, you have to do two cross products, you have to do like integrate dot products. Like it takes a lot of time to do all of this. And then the divergence theorem says, oh, this actually will be like a triple integral, and that's it. Like, so let's just like check it out because it is like a lot of time being saved if you can just find the flux using the divergence theorem. So like if at the level of the exams, if the problem wants you to find the flux using the divergence theorem, it literally says find the flux using the divergence theorem. So it's not like meant like it's not like a trap. Like it really just says use it. Like so. Like I don't even need that much space. Like you'll see, it's nothing like in terms of like. So now let's do the flux with the help of the divergence theorem. Okay, so again, the f, what is f here? Is negative y x z. What's the divergence of this f? Is the derivative with respect to x of negative y plus the derivative with respect to y of x plus the derivative with respect to z of z. So it's 0 plus 0 plus 1, which is just 1. So that's the divergence of this vector. And what the divergence theorem says is that the flux equals the triple integral of the divergence. So let me just remind you what the divergence theorem says, is that the flux, according to the divergence theorem, equals the triple integral of the divergence. Okay. But for this particular f, the divergence just happens to be 1. So you're going to integrate 1. How could we do the integral? We have to do it, like, you have to do it over the region that is enclosed by the surface. So over this region, you cylindrical, that makes sense. So what is the volume in cylindrical? R dz, dr d theta. What are the z bounds? Goes from z equals r squared to z equals 1. What are the hour bounds for this triple integral? From 0 to 1. And theta goes from 0 to pi. Okay, so like in the end, like it's kind of like easy, like it is like nothing to, there's nothing that depends on z. So it gives you the integral from 0 to 2 pi, 0 to 1 of r1 minus r squared dr d theta. And that is like, 2 pi, the integral from 0, 1 of like r minus r cubed dr. Like, there's something that depends on theta, so you can just do the integral out for theta first. So you get 2 pi times 1/2 minus 1/4. That's what you get if you like integrate it out. As always, yeah, so this is what gives you 1/4, so 2 pi over 4, which is pi over 2. And that's exactly that, right? So the difference is that the trade-off is that by using the divergence theorem, you really only get the total flux, right? So you cannot isolate the pieces, like, so you don't, from this pi over 2, we don't know what the individual contributions to the flux are. So we don't know that there was pi coming from one of the pieces of the surface and negative pi over 2 coming from the other one. But if you only care about the net flux, which in many situations you only do care about that, then that's like all that you need to know. Is that making sense? Questions about this? Okay, and just to finish, wrap this up, let me just write the Stokes theorem formula because otherwise I will feel bad if I don't write it. But like, again, I won't ask it on the exam, but at least I can tell you what it says because you already have all the ingredients to do it. But so Stokes theorem. But again, I won't ask it on the exam, so you can ignore it. So in Stokes theorem, you have a closed curve. And you have a vector f, and what Stokes theorem says is that if you want to find the work of f along the curve, what you do is like you can integrate the curl of the vector. Where you use any surface whose edge is that curve. So that's like the tricky part to explain, which is why I kind of like avoided like doing it like in class, like since we're like a bit of time. But like the idea of Stokes theorem is that if you think about it as a net, like like if you think of the curve being like the edges of this net, you choose like any surface whose edges are like those curves, and like you just integrate out the curl over the net itself. So that is kind of what you would do, like if you wanted to, if the curve were like the boundary of this net. The nice thing is that really any surface works. So like you can kind of like push the net like up and down, as long as you fix the edges, like it's still the same. It will still give you the same answer. So it's like there are more details if you really want to learn about it, like in one of the previous videos, in one of the videos I'll send on the announcement. But at least any surface whose edge is C. But the point is that you integrate the curl over a surface. So you know how to do these computations, is that before you were taking the dot, we were taking the dot product with F, now here you take the dot product with the curl. But it's kind of like the same idea. But again, I won't ask it on the exam, and if you want to learn more about it, yeah, you can just watch like some of the recordings from previous semesters. So let's finish here. I'll see you on Wednesday if you need to ask me questions about anything. And if not, I'll see you on Thursday. So don't forget to get here on Thursdays to do the exam.